Energy is one of the most fundamental concepts in physics, something that governs the behavior of everything in the universe, from the tiniest particles to the largest stars. For centuries, scientists believed that energy was a continuous quantity, flowing seamlessly without interruption, much like water in a river. Light, heat, and radiation were all thought to be smooth, unbroken phenomena. This assumption seemed perfectly reasonable because, in daily life, energy appears to be continuous. When we turn on a light, it brightens the room steadily. When we heat water, the temperature rises gradually. There is no hint, at first glance, that energy might behave differently at microscopic scales. Yet, as physics advanced into the late 19th and early 20th centuries, this classical picture began to unravel. The problem arose most clearly when scientists examined blackbody radiation. A blackbody is an idealized object that absorbs all radiation falling upon it and emits energy depending on its temperature. Classical physics predicted that as the temperature of a blackbody increased, it would radiate energy at all frequencies, with higher frequencies producing ever greater energy output. This prediction led to what was famously called the ultraviolet catastrophe, an absurd result suggesting that a blackbody would emit infinite energy at high frequencies. This was not just a theoretical inconvenience. Experiments consistently showed something completely different. Heated objects emitted radiation in discrete patterns, peaking at certain frequencies and dropping off at others, defying the smooth, continuous emission predicted by classical laws. It was in this context that the radical idea of quantized energy emerged. Rather than energy flowing in a continuous stream, it appeared to be emitted or absorbed in discrete packets. These packets, which would later be called quanta, represented the smallest possible units of energy exchange. The concept was revolutionary because it contradicted centuries of classical thought. Imagine pouring water into a glass in drops instead of a continuous stream. Each drop represents a fixed amount of energy, and you cannot have half a drop or a fraction of it in this view. Energy, at a fundamental level, was not infinitely divisible, but existed in these smallest units. This notion of quantization had profound implications. It provided a solution to the blackbody radiation problem by showing that high-frequency radiation required increasingly larger quanta of energy to be emitted. As a result, the amount of radiation at these frequencies would be limited, resolving the discrepancy between theory and observation. What had once seemed like a paradox, the ultraviolet catastrophe, was now explained elegantly through the idea that energy is inherently granular. The realization that the universe operates in these discrete steps rather than in smooth flows marked the beginning of a new era in physics, one in which the microscopic world obeyed rules radically different from those of classical mechanics. Beyond solving specific problems, the idea of quantized energy opened the door to a fundamentally new way of thinking about nature. It suggested that light, heat, and radiation could not simply be described as waves or continuous phenomena. They had particle-like properties, able to transfer energy only in fixed amounts. This challenged deeply held intuitions about the nature of reality and required scientists to develop new mathematical frameworks and experimental approaches to study the quantum world. It became clear that classical physics, while extremely successful at explaining macroscopic phenomena, was inadequate to describe processes at the atomic and subatomic scale. The impact of recognizing that energy is quantized cannot be overstated. It reshaped our understanding of chemistry, revealing that atoms and molecules interact by exchanging discrete amounts of energy. It redefined our understanding of light, leading directly to the concept of photons, the fundamental particles of electromagnetic radiation. It laid the groundwork for the later development of quantum mechanics, a framework that would come to dominate 20th century physics. The notion of energy quanta also inspired experiments that tested the limits of classical physics, ultimately confirming that at the microscopic level, the universe behaves in ways that are non-intuitive and inherently probabilistic. In everyday terms, the idea that energy is quantized may seem abstract, but it manifests in tangible ways. When we use lasers, semiconductors, or LEDs, we are harnessing processes that depend directly on the transfer of energy in discrete packets. The screens we look at, the lights that illuminate our homes, even the solar cells that power devices, all rely on principles that trace back to the understanding that energy comes in quanta. This single insight, that energy is not continuous but quantized, bridged the gap between observation and theory, linking the microscopic world to phenomena we can observe and manipulate in daily life. Thus, the recognition that energy is quantized represents not only a solution to a scientific problem, but a profound shift in the human understanding of nature. It reminds us that the universe is often more intricate and surprising than it appears, operating according to principles that may defy everyday intuition, but reveal an underlying order of elegance and precision. The discovery of quantized energy opened the door to the quantum revolution, forever changing physics and technology and providing a foundation for the remarkable scientific advances that define the modern world. The birth of quantum theory marked one of the most profound revolutions in the history of science, a turning point where the classical understanding of the universe began to give way to an entirely new framework. For centuries, physics had been dominated by Newtonian mechanics, a system that explained motion, forces, and energy in terms of continuous laws and predictable patterns. Light was understood purely as a wave, matter as a continuous substance, and energy as flowing seamlessly through space. This classical approach worked extraordinarily well for everyday phenomena, from the motion of planets to the mechanics of machines. Yet, when scientists turned their attention to the behavior of atoms, molecules, and light at microscopic scales, the classical theories failed dramatically. Observations could not be reconciled with the predictions of Newtonian physics. This gap between theory and experiment created a crisis, a puzzle that would eventually give rise to a radical new way of thinking. The central problem lay in understanding how energy is emitted and absorbed at atomic and subatomic levels. Experiments with heated objects revealed patterns of radiation that classical physics could not explain. The spectrum of a blackbody, for instance, displayed distinct peaks rather than the smooth distribution predicted by traditional laws. Scientists found themselves confronted with the ultraviolet catastrophe, a theoretical prediction suggesting infinite radiation at high frequencies, clearly at odds with experimental results. This glaring discrepancy highlighted a fundamental limitation of the classical world. While it excelled at describing macroscopic phenomena, it was inadequate for the microscopic world. Something had to change. The revolutionary idea was that energy does not flow continuously, but is emitted and absorbed in discrete packets. This concept, which became the cornerstone of quantum theory, fundamentally altered how we understand the interactions of matter and energy. Each packet, later called a quantum, represents the smallest unit of energy that can be exchanged. The realization that energy could only exist in these discrete amounts was counterintuitive, challenging centuries of assumptions about the continuous nature of the physical world. Unlike classical systems, where energy could take any value. In this new view, energy comes in specific, indivisible units. This insight provided a way to reconcile experimental observations with theory, solving problems that had previously seemed unsolvable. Quantum theory did not emerge in isolation. It built on careful observation, experimentation, and mathematical insight. By analyzing Blackbody radiation and the emission of light, scientists developed a new formula that could accurately predict the behavior of energy at different frequencies. This formula introduced a constant, a fixed value that linked energy and frequency, providing a quantitative framework for understanding discrete energy exchanges. With this development, the principles of classical physics were supplemented, rather than discarded entirely, by a new set of rules that governed atomic and subatomic behavior. The birth of quantum theory also challenged the way scientists thought about the very nature of light and matter. In the classical view, light was purely a wave, capable of spreading continuously through space. Quantum theory suggested something profoundly different. Light could behave as both a wave and a particle. This duality, though difficult to visualize, explained experimental results that had long puzzled physicists, such as the photoelectric effect, where light striking a metal surface could eject electrons. The discrete nature of energy exchange provided a mechanism for understanding this phenomenon, demonstrating that light transfers energy in quantized amounts. The implications of quantum theory extended far beyond solving isolated problems. It provided a framework for understanding atomic structure, chemical bonding, and the behavior of matter at its most fundamental level. The concept of quantized energy levels explained why electrons occupy specific orbits around the nucleus, why atoms emit light at discrete frequencies, and why chemical reactions occur in predictable ways. In essence, quantum theory revealed that the universe is governed by underlying patterns and constraints that are invisible to classical observation, but profoundly affect everything from smallest particles to the technology that powers modern life. The introduction of quantum theory also transformed the philosophy of science. It challenged the deterministic world view that had dominated for centuries, suggesting that at the microscopic level, probabilities and uncertainties govern behavior. Nature, it seemed, does not always conform to intuition. Instead of continuous, predictable flows, processes unfold in discrete, sometimes surprising steps. This shift required scientists to adopt new mathematical tools and conceptual frameworks, laying the groundwork for the development of modern quantum mechanics. Even today, the birth of quantum theory remains a defining moment in science. It opened doors to technologies that were unimaginable in the classical era. Lasers, semiconductors, medical imaging, and quantum computing all rely on the principles that emerged from the recognition that energy is quantized, and that matter exhibits behavior that defies classical expectations. The theory also inspired generations of physicists to probe deeper, exploring the probabilistic and counterintuitive nature of reality, and to ask questions about the universe that classical physics could never address. The birth of quantum theory reminds us that science is a dynamic process, one that evolves in response to evidence and insight. It demonstrates that the universe is far more intricate than it may appear, governed by rules that are subtle, discrete, and profoundly interconnected. By acknowledging that energy exists in quanta and that the microscopic world behaves according to its own set of laws, scientists were able to unlock mysteries that had eluded understanding for centuries. This moment did not just solve a problem. It reshaped the very foundation of physics and transformed our understanding of reality itself, opening a gateway to the modern world of quantum science and technology. The Blackbody radiation problem represents one of the most intriguing challenges in the history of physics, a puzzle that puzzled scientists for decades and ultimately paved the way for the birth of quantum theory. At the heart of this issue was the observation that objects emit light and heat when heated, a phenomenon familiar to anyone who has seen a piece of metal glow red or a stove heating a pan. Classical physics, with its laws rooted in continuous energy and wave theory, predicted a specific behavior for these emissions. According to these models, as the temperature of an object increased, the intensity of emitted radiation should rise smoothly across all frequencies. In particular, at higher frequencies, the energy should increase without limit. This prediction, however, starkly contradicted experimental observations. Scientists noted that instead of energy increasing endlessly at high frequencies, radiation intensity peaked at certain frequencies and then declined, creating a distribution that could not be reconciled with existing theories. This glaring discrepancy became known as the Blackbody radiation problem. A blackbody, in theoretical terms, is an idealized object that absorbs all radiation incident upon it and emits energy solely as a function of its temperature. In practice, no physical object behaves as a perfect blackbody, but many materials approximate this behavior closely enough to allow for meaningful experimentation. As scientists measured the radiation emitted by these objects at various temperatures, they encountered patterns that classical physics could not explain. The ultraviolet catastrophe, a term that vividly captures the paradox, suggested that the energy radiated at short wavelengths would approach infinity, a result that was clearly impossible. The failure of classical physics in this context highlighted a critical limitation. The laws that accurately described macroscopic phenomena broke down when applied to the microscopic world of atoms and molecules. The Blackbody radiation problem forced scientists to reconsider the nature of energy itself. Traditional physics assumed energy could vary continuously, allowing any value, no matter how small. However, the experimental evidence implied that energy could only be emitted or absorbed in fixed quantities, or quanta. This shift in thinking was radical. It suggested that the smooth flow of energy imagined in classical physics did not exist at microscopic scales. Instead, energy exchanges occur in discrete steps, much like climbing a staircase rather than sliding up a ramp. Each step represents a specific amount of energy that cannot be subdivided further in the process of emission or absorption. This insight was revolutionary, opening the door to a fundamentally new understanding of the physical world. The solution to the Blackbody radiation problem required both creative thinking and precise mathematical formulation. By introducing the concept of quantized energy levels and establishing a constant that related energy to frequency, scientists were able to derive an equation that accurately described the observed spectrum of emitted radiation. This approach demonstrated that at higher frequencies, the required energy quanta were so large that emissions became increasingly unlikely, naturally explaining why the radiation intensity declined rather than skyrocketing to infinity. In doing so, the paradox of the ultraviolet catastrophe was resolved, and a new, predictive framework emerged. This framework did not merely patch an old theory. It fundamentally altered our understanding of energy, light, and matter. The implications of solving the Blackbody radiation problem extended far beyond a single experimental anomaly. It revealed that the microscopic world operates according to principles that differ significantly from our macroscopic intuition. Energy is not a smooth continuum, but comes in quantized packets, a realization that would underpin the development of quantum mechanics. This discovery reshaped atomic theory, providing an explanation for phenomena such as discrete spectral lines in atomic emissions. It also offered insights into the behavior of electrons, chemical reactions, and the interaction of light with matter. Essentially, the Blackbody radiation problem served as a gateway, guiding physicists from classical mechanics into the rich and often counterintuitive landscape of quantum physics. The historical significance of this problem cannot be overstated. It challenged deeply held assumptions, demonstrating that scientific progress often requires questioning even the most established principles. The resolution of the Blackbody radiation problem was not only a triumph of theoretical insight, but also a testament to the power of experimental observation. By carefully measuring the behavior of heated objects and comparing these results with predictions, scientists revealed the inadequacy of classical theories and laid the foundation for a new paradigm. This process exemplifies the essence of scientific inquiry, the willingness to follow evidence wherever it leads, even if it demands a radical rethinking of the natural world. Moreover, the lessons learned from Blackbody radiation continue to influence modern science and technology. The principles derived from understanding quantized energy emissions underpin the operation of lasers, LEDs, and various photonic devices. They inform research in thermodynamics, materials science, and astrophysics, influencing everything from the study of stars to the design of high-efficiency solar cells. By resolving a problem that initially seemed purely theoretical, scientists unlocked practical applications that permeate contemporary life, illustrating the deep connection between fundamental research and technological innovation. The Blackbody radiation problem also highlights the iterative nature of scientific discovery. Initial classical models were not discarded lightly. They were examined, tested, and found insufficient. The shift to a quantum perspective did not negate earlier knowledge, but rather extended it, showing that classical laws remain effective in many contexts while revealing their limitations in others. This nuanced understanding is a hallmark of mature scientific thinking, emphasizing both continuity and innovation. Ultimately, the Blackbody radiation problem exemplifies the power of questioning, observation, and theoretical creativity. It represents the moment when physics moved beyond the familiar and ventured into the unknown, embracing a new vision of the universe where energy is quantized, nature is discrete and classical. Intuition must be supplemented by a deeper understanding. The resolution of this problem was not just a solution to an experiment. It was a gateway into the quantum realm, forever changing the way humanity perceives the workings of the cosmos. The introduction of Planck's constant marked a pivotal moment in the development of modern physics, a subtle yet profound insight that transformed the way scientists understood energy, light, and the fundamental behavior of matter. In classical physics, energy was assumed to flow smoothly, continuous, and infinitely divisible, without any inherent limitation on its quantity. This perspective had served science well for centuries, explaining everything from the motion of planets to the dynamics of fluids. Yet, as experiments probing atomic and subatomic phenomena became more precise, the inadequacy of this classical assumption became increasingly clear. Observations of radiation emitted by heated objects and the peculiar behavior of light at microscopic scales revealed inconsistencies that could not be explained without a new approach. It was in this context that Planck introduced a groundbreaking concept: the existence of a constant that links energy to the frequency of radiation, now known universally as Planck's constant. Planck's constant, symbolized by the letter h, is a small yet fundamental number that quantifies the relationship between the energy of a photon and the frequency of the electromagnetic wave it represents. The equation E equals hf succinctly captures this relationship, where E represents the energy of a single quantum of radiation, F is the frequency of the associated wave, and h serves as the bridge between the two. This deceptively simple equation carries profound implications, asserting that energy is not continuous but exists in discrete packets called quanta. Each quantum represents a minimum indivisible amount of energy that can be absorbed or emitted. The introduction of Planck's constant was not merely a mathematical convenience. It embodied a fundamental truth about the way the universe operates at microscopic scales, revealing the granularity of energy itself. Before this insight, scientists struggled to reconcile the observed behavior of blackbody radiation with classical theory. According to traditional physics, the energy emitted by a heated object should increase indefinitely at high frequencies, resulting in the ultraviolet catastrophe. The introduction of quantized energy, formalized through Planck's constant, provided an elegant solution. At higher frequencies, the energy required for each quantum becomes progressively larger, making it increasingly unlikely that such high-energy quanta would be emitted. This simple yet powerful idea resolved the paradox and allowed scientists to derive accurate predictions for the distribution of radiation across all frequencies. The constant itself, though incredibly small, plays a central role in defining the scales at which quantum effects become significant. The significance of Planck's constant extends far beyond blackbody radiation. It serves as the foundation for the entire edifice of quantum mechanics, influencing how we understand atomic structure, chemical interactions, and the behavior of subatomic particles. By establishing a fixed relationship between energy and frequency, the constant imposes a discrete framework on processes that had previously been thought of as continuous. Electrons in atoms, for instance, can only occupy specific energy levels, absorbing or emitting energy in precise amounts when transitioning between these levels. Without Planck's constant, the quantization of these energy levels would be inexplicable, and the stability of matter as we know it would remain a mystery. The discovery of Planck's constant also had profound implications for the study of light. Classical wave theory treated light as an unbroken, continuous phenomenon, capable of varying in intensity without restriction. Yet experiments, including the photoelectric effect, demonstrated that light interacts with matter in discrete units. A photon, the fundamental particle of light, carries energy directly proportional to its frequency, a relationship governed by Planck's constant. This understanding reconciled wave, like and particle-like behaviors of light, giving rise to the concept of wave-particle duality and opening the door to a deeper comprehension of electromagnetic radiation. Technologically, the influence of Planck's constant is immense, even if it is not immediately visible in everyday life. The principles derived from this constant underpin modern electronics, lasers, quantum computing, and a host of devices that rely on precise manipulation of energy at microscopic scales. Semiconductors, which form the backbone of all modern computing devices, operate based on transitions between quantized energy levels. Lasers, which revolutionized communication, medicine, and industry, depend on the controlled emission of photons whose energies are defined by Planck's constant. In essence, this tiny number, invisible to the naked eye, governs the behavior of countless technologies that shape contemporary life. Planck's constant also represents a philosophical shift in our understanding of the universe. It underscores that nature at its most fundamental level is not smooth and continuous, but discrete and quantized. This insight challenges classical intuitions and invites a more nuanced appreciation of reality. It illustrates that even phenomena that appear seamless to human perception, such as light and heat, operate according to rules that are precise, granular, and mathematically elegant at microscopic scales. By codifying this principle into a constant, Planck provided scientists with a tool to navigate the emerging world of quantum mechanics, transforming both theoretical understanding and experimental practice. The introduction of Planck's constant can be seen as the keystone of the quantum revolution. It resolved long-standing paradoxes, offered a quantitative framework for energy quantization, and laid the groundwork for a century of discoveries that continue to redefine science. From the structure of atoms to the development of quantum technologies, this single constant embodies the discrete nature of the universe, revealing patterns and limitations that were previously invisible. It is a testament to the power of insight, observation, and mathematical rigor, demonstrating how a fundamental truth, once recognized, can illuminate the workings of the cosmos and reshape the trajectory of human knowledge. The relationship between energy and frequency is one of the most profound revelations in the history of physics, a simple yet revolutionary concept that reshaped the understanding of light, matter, and the behavior of the universe at its most fundamental level. Before this discovery, classical physics treated energy as a continuous quantity, able to vary in an unbroken and limitless manner. Waves of light were seen as purely continuous oscillations, spreading smoothly through space without limitation. Heat, radiation, and light were all understood in terms of classical wave mechanics, which could predict macroscopic phenomena with remarkable accuracy. Yet, when physicists examined the emission and absorption of energy on the atomic scale, this classical understanding failed dramatically. Experiments revealed patterns that could not be explained unless energy itself was fundamentally linked to frequency and existed in discrete packets. The energy-frequency relationship, captured elegantly in the equation E=hf, formalizes the idea that the energy of a quantum of electromagnetic radiation is directly proportional to its frequency. Here, E represents the energy of a single quantum, F denotes its frequency, and H is Planck's constant, a fundamental value that serves as the bridge between energy and frequency. This simple proportionality carries profound implications. It asserts that higher frequency radiation, such as ultraviolet or X-rays, carries more energy per quantum than lower frequency radiation, such as infrared or radio waves. The concept provides a clear explanation for phenomena that classical physics could not account for, resolving paradoxes and laying the foundation for quantum mechanics. This relationship is particularly important when considering the emission of light and the behavior of atoms. Classical theory predicted that energy could be radiated in arbitrary amounts, but experiments consistently showed that electrons absorb or emit energy in precise increments corresponding to discrete energy levels. When an electron jumps from one energy level to another within an atom, the difference in energy is released or absorbed as a quantum of light, or photon. The frequency of the emitted photon is directly determined by the energy difference between these levels, a relationship governed precisely by E=hf. This discovery revealed a hidden order in the atomic world. Energy transitions are quantized, predictable, and inherently linked to the oscillatory nature of light. The energy-frequency relationship also provided a solution to long-standing puzzles such as the photoelectric effect. When light strikes a metal surface, electrons are ejected, but classical physics could not explain why low-frequency light regardless of intensity, failed to release electrons, while higher frequency light succeeded even at lower intensity. Understanding that the energy of a photon depends on its frequency clarified this mystery. Only photons with sufficient energy, determined by their frequency, could impart enough energy to free an electron from the metal. This insight confirmed that light behaves not only as a wave, but also as a particle, and that energy is transferred in discrete units rather than continuously. It was a decisive step toward the broader acceptance of quantum theory, fundamentally altering the conceptual framework of physics. The implications of the energy-frequency relationship extend far beyond atomic behavior and laboratory experiments. In practical terms, it informs technologies that define the modern world. Lasers, for example, operate on the principle of stimulated emission, where photons of specific frequency, and therefore specific energy, interact with atoms to produce coherent light. The color of the laser, its intensity, and its energy are all determined by the precise energy-frequency relationship. Similarly, photovoltaic cells convert light into electricity by absorbing photons whose energy corresponds to the frequency of incoming sunlight, illustrating the practical application of this principle in renewable energy technologies. Even medical imaging techniques, such as X-rays and MRI, rely on understanding how energy and frequency interact at atomic and molecular levels. On a deeper scientific level, the energy-frequency relationship reveals the interconnectedness of time, space, and energy. Since frequency is inversely related to wavelength, and wavelength is a spatial property of a wave, the proportionality of energy and frequency links temporal oscillations with the amount of energy transferred. This relationship is fundamental to the concept of wave-particle duality, where particles such as photons exhibit both wave-like and particle-like characteristics. The ability to quantify energy through frequency provides a mathematical framework for predicting the behavior of light and matter under a variety of conditions, from simple atomic transitions to the complex interactions observed in high-energy physics and cosmology. The discovery of the energy-frequency relationship also challenged the philosophical assumptions of classical physics. It revealed that the universe at its most fundamental level does not behave in a smooth, continuous manner, but rather in discrete, quantized steps. Energy is not infinitely divisible in interactions. It is constrained by the properties of the quantum world. This realization demanded a radical rethinking of the laws of nature, ultimately giving rise to a more sophisticated, probabilistic understanding of reality. Concepts like uncertainty, probability, and quantization, which are now central to quantum mechanics, emerge naturally from this simple proportionality between energy and frequency. In essence, the energy-frequency relationship bridges the visible, tangible world and the invisible, intricate world of quantum phenomena. It connects the brightness of a star, the color of light, and the emission of electrons to fundamental principles that govern the universe. By understanding that the energy of a quantum depends on its frequency, scientists unlocked a framework that explained countless phenomena, resolved paradoxes, and enabled the technological innovations that shape modern society. This principle continues to inspire research, guiding inquiries into quantum computing, particle physics, and the exploration of cosmic radiation, illustrating that a single relationship can illuminate the workings of the universe on scales both microscopic and astronomical. The concept of wave-particle duality represents one of the most intriguing and counterintuitive discoveries in the history of physics, fundamentally altering how we understand light, energy, and matter. Before the emergence of quantum theory, classical physics held a rigid distinction between waves and particles. Waves were continuous disturbances that traveled through space, like ripples on a pond or sound propagating through air. Particles, on the other hand, were localized entities with mass, moving through space along predictable trajectories. Light was long considered purely a wave phenomenon, described mathematically by Maxwell's equations, which explained reflection, refraction, interference, and diffraction. Matter, including electrons, atoms, and molecules, was treated as composed of discrete particles obeying Newtonian mechanics. This clear separation seemed logical and consistent with observations at macroscopic scales. However, experiments at the turn of the 20th century began to reveal a more complex and nuanced reality. The seeds of wave-particle duality were planted through the study of light. Experiments such as the photoelectric effect demonstrated that light interacts with matter not as a smooth, continuous wave, but as a stream of discrete energy packets called photons. In these experiments, when light of sufficient frequency strikes a metal surface, electrons are ejected. Classical wave theory predicted that increasing the intensity of light, regardless of its frequency, should eventually release electrons, yet this did not occur. Instead, only light above a certain frequency threshold caused electron emission, and the energy of emitted electrons depended on the light's frequency, not its intensity. This observation suggested that light behaves as a particle in these interactions, transferring energy in quantized units, and challenged the long-held assumption that it was purely a wave phenomenon. At the same time, experiments with interference and diffraction confirmed that light retained its wave-like properties. When light passes through two closely spaced slits, it produces a characteristic pattern of alternating bright and dark fringes on a screen, a behavior explained only by wave interference. These seemingly contradictory observations that light exhibits both particle-like and wave-like behavior gave rise to the concept of wave-particle duality. Rather than being exclusively a wave or a particle, light possesses both characteristics, manifesting differently depending on how it is observed. This duality is not merely a theoretical curiosity. It reflects the underlying principles of nature, revealing that the microscopic world does not conform to classical intuitions. The implications of wave-particle duality extend far beyond light. Louis de Broglie, a French physicist, proposed that matter itself exhibits wave-like properties. Electrons, protons, and even larger particles can behave as waves under appropriate conditions, exhibiting interference and diffraction patterns. This was confirmed through experiments such as electron diffraction, in which beams of electrons passing through a crystal produced patterns characteristic of wave interference. The recognition that both light and matter display dual behavior revolutionized physics, demonstrating that the universe at its most fundamental level does not adhere strictly to classical categories. Instead, entities such as photons and electrons are described by a richer, more complex set of principles, governed by quantum mechanics. Wave-particle duality also reshaped the way scientists understand energy transfer and interactions. Photons carry energy proportional to their frequency, while their wave-like properties determine phenomena such as interference and diffraction. Similarly, electrons have mass and can be localized as particles, but they also exhibit wave characteristics that allow them to occupy discrete energy levels in atoms, form standing wave patterns, and produce diffraction effects. This dual behavior is essential for understanding the structure of atoms, chemical bonding, and the emission of spectral lines. The quantized nature of energy, combined with wave-particle duality, provides a unified framework for describing both the discrete and continuous aspects of physical phenomena. In practical terms, wave-particle duality underpins many modern technologies. Electron microscopes rely on the wave properties of electrons to achieve resolutions far beyond the limits of optical microscopes, allowing scientists to observe structures at the atomic level. Lasers exploit the wave coherence of photons while also taking advantage of their quantized energy to produce precise and intense beams of light. Quantum computing leverages the dual behavior of particles to encode and manipulate information in ways that classical systems cannot, opening doors to computation on an unprecedented scale. These applications illustrate that wave-particle duality is not an abstract theoretical idea, but a fundamental principle with tangible consequences for technology and society. Philosophically, wave-particle duality challenges human intuition, showing that reality at the quantum level is not easily visualized or categorized. It underscores the limitations of classical concepts and emphasizes that observation plays a central role in defining the behavior of quantum systems. The duality also highlights the probabilistic nature of the quantum world, where entities do not have well-defined positions or momenta until measured. This insight paved the way for further developments in quantum mechanics, including the uncertainty principle, quantum superposition, and the broader understanding of matter-energy interactions. Ultimately, wave-particle duality exemplifies the elegance and complexity of the universe. It bridges phenomena that appear contradictory, revealing a deeper coherence in the laws of nature. By embracing the dual nature of light and matter, scientists developed a framework that explains atomic structure, energy quantization, and the behavior of fundamental particles. This principle continues to guide research and innovation, from nanotechnology to high-energy physics, demonstrating that even the most counterintuitive ideas can lead to profound insights and transformative discoveries. The impact of quantum discoveries on atomic theory represents one of the most transformative shifts in scientific understanding, fundamentally altering how we perceive the structure and behavior of matter. Prior to the advent of quantum concepts, atoms were largely mysterious entities, thought to be indivisible particles or tiny spheres governed by classical mechanics. Early models, such as the plum pudding model, pictured atoms as diffuse positive matter with negatively charged electrons embedded randomly within. While these models could explain some observations, they failed to account for experimental results that probed deeper into atomic structure. Spectral lines, for example, revealed discrete frequencies of light emitted or absorbed by atoms, a phenomenon that classical theory could not reconcile. The recognition that energy is quantized offered a pathway to understanding these atomic behaviors and marked the beginning of a new era in atomic theory. The central breakthrough was the realization that electrons within an atom do not occupy arbitrary energy states, but instead exist in specific, discrete levels. Classical physics had envisioned electrons orbiting the nucleus much like planets around the Sun, with energy varying continuously depending on speed and distance. However, experiments demonstrated that electrons could only reside in certain allowed energy levels, and any transition between these levels involved the absorption or emission of energy in fixed quantities. This quantization of energy explained the existence of spectral lines. When an electron jumps from a higher energy level to a lower one, it emits a photon with energy precisely equal to the difference between the two levels. Conversely, The absorption of a photon allows an electron to move to a higher level, but only if the photon's energy matches the required quantum exactly. This insight provided the missing link between observed atomic spectra and theoretical models of the atom. The adoption of quantized energy levels revolutionized the understanding of atomic structure. Electrons were no longer envisioned as particles moving in arbitrary paths around the nucleus, but rather as existing in well-defined orbits or states with specific energies. These discrete orbits, later formalized in more advanced quantum models, explained why atoms are stable and do not collapse despite the attractive forces between electrons and the nucleus. By allowing only certain energy states, nature imposes a structure that prevents electrons from spiraling into the nucleus, a puzzle that had perplexed classical physics. This understanding not only clarified the internal architecture of atoms, but also laid the foundation for explaining chemical behavior, bonding patterns, and the formation of molecules. The influence of quantum ideas extended beyond individual atoms to the broader behavior of matter. By recognizing that energy exchanges occur in discrete units, scientists could explain phenomena such as ionization, where electrons are removed from atoms, and excitation, where electrons are promoted to higher energy states. These processes are fundamental to understanding chemical reactions, electrical conductivity, and the emission of light in gases and solids. In essence, the quantization of energy provided a unifying framework that connected atomic theory, spectroscopy, and chemical behavior, offering a coherent explanation for a wide range of previously puzzling observations. Moreover, these concepts had profound implications for the development of new atomic models. Niels Bohr, building on the idea of quantized energy levels, proposed a model in which electrons occupy fixed orbits around the nucleus, with radiation emitted or absorbed only when electrons transition between these orbits. This model successfully explained the discrete spectral lines of hydrogen and provided a tangible, predictive framework for atomic physics. Although later refined by the development of quantum mechanics and the Schrödinger equation, Bohr's model demonstrated the power of incorporating quantized energy into atomic theory and illustrated how theoretical innovation could resolve long-standing experimental mysteries. The quantization of energy also redefined the relationship between light and matter. When electrons transition between energy levels, the energy of the emitted or absorbed photon is directly related to the frequency of the radiation, as captured by the relationship E equals hf. This connection reinforced the idea that light itself is quantized, linking the behavior of photons to the internal structure of atoms. Spectroscopy, the study of these emissions and absorptions, became a precise tool for probing atomic structure and chemical composition, transforming both theoretical and applied science. Observations of spectral lines from distant stars, for example, allow scientists to determine their chemical makeup, temperature, and movement, demonstrating the wide-reaching implications of understanding atomic quantization. Technologically, the implications of quantized atomic energy levels are profound. Lasers, semiconductors, LEDs, and numerous electronic devices rely directly on controlled transitions of electrons between energy states. The ability to manipulate these transitions with precision has revolutionized communication, medicine, and computing. Even the functioning of everyday technologies such as fluorescent lights and solar cells depends on the principles of atomic energy quantization, illustrating how a fundamental discovery about the microscopic world shapes the macroscopic reality of human life. Beyond its practical applications, the quantization of atomic energy reshaped philosophical and scientific perspectives. It demonstrated that the universe operates according to discrete, rather than purely continuous, principles. It challenged the deterministic view of classical mechanics, introducing a probabilistic framework where energy, matter, and light follow precise rules yet exhibit behaviors that defy intuitive understanding. This shift set the stage for the broader development of quantum mechanics, including concepts such as wave, functions, uncertainty, and superposition, which continue to underpin modern physics. Ultimately, the quantization of atomic energy levels provided a coherent and predictive framework that resolved numerous experimental paradoxes and transformed the study of matter. By revealing the ordered, discrete nature of energy transitions within atoms, scientists could explain spectral lines, chemical properties, and atomic stability. These discoveries bridged observation and theory, creating a foundation for technological innovation and deepening our understanding of the universe. The influence of quantized atomic energy is still felt today, from the smallest electronic devices to the exploration of distant stars, highlighting the enduring power of this revolutionary insight in shaping both science and society. The concept of a quantum leap, or sudden energy transition, represents one of the most remarkable and non-intuitive aspects of quantum physics, fundamentally transforming our understanding of atomic behavior. In classical physics, change is perceived as continuous, gradual, and smooth. Planets orbit the sun in predictable paths. The swing of a pendulum traces an unbroken curve, and energy flows seamlessly through systems. Yet, at the microscopic level of atoms and electrons, this intuitive notion of continuity breaks down. Electrons do not move gradually from one energy state to another. Instead, they shift instantaneously, leaping from one discrete energy level to another without existing in between. This phenomenon, often called a quantum leap or quantum jump, defied classical expectations and reshaped how scientists conceptualize atomic interactions. The discovery of quantum leaps arose from the study of atomic spectra and the behavior of electrons within atoms. When atoms are energized, either by heat, electricity, or light, their electrons move between allowed energy levels. Classical physics could not account for the precise frequencies of light emitted or absorbed during these transitions, but the concept of quantized energy states provided the solution. An electron residing in a lower energy level cannot gradually climb to a higher level. It requires a precise amount of energy corresponding to the difference between the two levels. If the input energy does not match this gap exactly, the electron remains in its original state. Once the energy threshold is met, the electron instantaneously jumps to the higher level, emitting or absorbing a photon with energy determined by the relationship E equals hf, where h is Planck's constant and f is the frequency of the photon. This leap occurs without traversing intermediate energy states, a phenomenon that is both counterintuitive and foundational to quantum theory. Quantum leaps provide a vivid explanation for the discrete lines observed in atomic spectra. Each spectral line corresponds to a specific transition between quantized energy levels, representing the emission or absorption of photons with particular energies. These lines are not continuous. They appear as distinct bands that can be measured precisely, revealing the ordered, discrete nature of atomic energy states. The concept of quantum jumps thus bridges the microscopic processes occurring within atoms to the macroscopic observations of emitted or absorbed light, allowing scientists to map the structure and behavior of electrons with remarkable accuracy. The implications of quantum leaps extend beyond the emission of light. They form the basis for understanding chemical reactions, molecular interactions, and the behavior of materials at the atomic level. Electrons moving between energy levels dictate how atoms bond, how energy is stored and released in chemical processes, and how materials respond to external stimuli such as heat or electromagnetic fields. The sudden, discrete nature of these transitions also explains why atoms are stable. Electrons cannot gradually spiral into the nucleus because only specific energy states are permitted. This stability is a direct consequence of the quantized framework of atomic energy levels. Quantum leaps also reveal the probabilistic nature of quantum mechanics. While the energy associated with a leap is precisely defined, the timing of when a particular electron will make the transition is inherently uncertain. This introduces an element of randomness, reflecting a universe that does not operate in strictly deterministic ways at microscopic scales. Experiments such as observing single electron transitions show that while the energy and final states are predictable, the exact moment of a quantum jump cannot be determined with certainty. This probabilistic aspect challenged centuries of classical assumptions and opened the door to a new, more nuanced understanding of physical reality. Technologically, the principle of quantum leaps has far-reaching consequences. Lasers, for instance, operate by inducing electrons to undergo synchronized transitions between energy levels, emitting photons in coherent waves. The precise control of these transitions allows lasers to produce highly focused, intense beams of light, enabling applications in medicine, communication, manufacturing, and scientific research. Similarly, fluorescent lights, LEDs, and even solar panels rely on the principles of electrons jumping between energy states to generate light or electricity efficiently. In each case, the macroscopic functionality of the device depends directly on the microscopic phenomenon of quantized, instantaneous transitions. Quantum leaps also provide insight into fundamental questions about energy transfer. Unlike classical systems, where energy changes gradually, the energy associated with quantum jumps is discrete, ensuring that energy is neither lost nor dispersed in fractional amounts. This principle underlies the conservation of energy in quantum processes and offers a framework for understanding interactions at the smallest scales, from atomic collisions to photon emission. It also forms the conceptual foundation for more advanced quantum phenomena, including tunneling, superposition, and entanglement, which continue to revolutionize modern physics and technology. Philosophically, quantum leaps challenge our perception of continuity and time. They illustrate that nature operates differently at the quantum level, with processes occurring in sudden, discrete steps rather than smooth transitions. This insight forces a reconsideration of intuitive notions of causality, motion, and change, demonstrating that the microscopic world obeys principles that are fundamentally distinct from everyday experience. It highlights the need for new conceptual frameworks, mathematical models, and experimental approaches to fully grasp the behavior of matter and energy at atomic and subatomic scales. Ultimately, quantum leaps exemplify the elegance and precision of the quantum world. They reveal that the universe is structured in discrete, ordered steps, where energy transitions occur instantaneously and predictably, even if their timing remains probabilistic. By understanding these sudden jumps, scientists gain the ability to predict spectral lines, explain atomic stability, design modern technologies, and explore the deeper principles governing matter and light. Quantum leaps are not merely theoretical curiosities. They are tangible, observable phenomena that illuminate the intricate, counterintuitive, and profoundly ordered nature of the microscopic universe. The concept of energy quantization in electromagnetic radiation marked a profound turning point in our understanding of light and its interaction with matter, revealing that light is not simply a continuous wave, but consists of discrete packets of energy called photons. Classical physics had long treated light purely as a wave phenomenon, capable of spreading smoothly through space, bending around obstacles, and interfering with itself. These wave properties explained many observable phenomena such as reflection, refraction, diffraction, and interference. Yet certain experimental results resisted classical explanation. One of the most striking of these was the photoelectric effect, in which light striking a metal surface causes the emission of electrons. The behavior observed in these experiments challenged the continuous wave model, suggesting that light itself has a particle-like component with quantized energy. The photoelectric effect demonstrated that the energy of emitted electrons depends not on the intensity of the light, but on its frequency. According to classical wave theory, increasing the brightness of light should provide enough energy to release electrons regardless of frequency. But experiments revealed that no electrons were emitted below a certain threshold frequency, no matter how intense the light. Conversely, light above this frequency threshold caused electrons to be ejected immediately, even at low intensity. This behavior could only be explained if light were composed of discrete energy packets, with each packet carrying energy proportional to its frequency, as expressed in the relationship E equals hf, where h is Planck's constant and f is the frequency. In essence, light acts as a particle when transferring energy to matter, with each photon delivering a fixed, quantized amount of energy. This discovery fundamentally altered the conceptual framework of physics, revealing the dual nature of light. It behaves as a wave in some circumstances, such as when it produces interference patterns, yet it exhibits particle-like properties when interacting with matter at microscopic scales. This wave-particle duality challenged centuries of classical intuition, demonstrating that at the quantum level, physical phenomena do not conform to everyday expectations. The idea that light consists of discrete quanta provided a mechanism to reconcile experimental results with theory, explaining not only the photoelectric effect, but also other phenomena such as Blackbody radiation and atomic spectral lines. The implications of energy quantization extend far beyond the emission of electrons from metal surfaces. Understanding that photons carry energy in discrete packets allows scientists to explain the precise frequencies of light absorbed or emitted by atoms. When electrons in an atom transition between energy levels, they absorb or emit photons with energies exactly corresponding to the difference between those levels. This quantized exchange of energy accounts for the distinct spectral lines observed in atomic spectra, providing a detailed map of atomic structure. By analyzing these spectral lines, scientists can determine the composition, temperature, and motion of distant stars, connecting the microscopic properties of atoms to macroscopic observations of the universe. Quantized electromagnetic radiation also underpins a wide range of modern technologies. Lasers, for example, rely on the emission of photons from electrons transitioning between discrete energy levels. The coherence and intensity of laser light depend on controlling these transitions precisely, enabling applications in medicine, telecommunications, manufacturing, and scientific research. Photovoltaic cells, which convert sunlight into electricity, exploit the fact that photons carry specific energy, allowing electrons to be excited across energy gaps and produce electric current. LEDs, fluorescent lights, and other devices similarly rely on the principles of photon energy quantization to produce light efficiently. These applications demonstrate that a seemingly abstract theoretical insight has direct and pervasive practical consequences. The discovery of quantized energy also led to a deeper understanding of the interaction between light and matter. Photons do not merely impart energy. They mediate fundamental processes in atoms and molecules, enabling chemical reactions, electron excitation, and ionization. The quantized nature of these interactions ensures that energy is exchanged in exact amounts, preserving the conservation of energy in atomic and molecular systems. This principle underlies the functioning of semiconductors, the behavior of lasers, and even biological processes such as photosynthesis, illustrating the universality of quantized energy transfer across diverse systems. Philosophically, the quantization of light challenged the deterministic world view of classical physics. The discrete nature of photon energy, combined with the probabilistic timing of photon emission and absorption, introduced inherent uncertainty into the behavior of microscopic systems. This led to the development of quantum mechanics, a framework that describes nature not in terms of continuous, predictable trajectories, but as probabilities, amplitudes, and discrete energy levels. The quantization of electromagnetic radiation thus represents both a scientific and conceptual revolution, reshaping our understanding of reality at its most fundamental level. The recognition that light is quantized also opened the door to new lines of inquiry in fundamental physics. It provided a foundation for the development of quantum electrodynamics, which describes how light and matter interact, and later contributed to our understanding of particle physics, quantum information, and photonics. By revealing the discrete nature of energy and light, scientists gained a powerful tool for probing the atomic and subatomic world, enabling experiments that test the limits of physical laws and explore the boundaries between classical and quantum behavior. Ultimately, the quantization of electromagnetic radiation illuminates the intricate and ordered structure of the universe. It bridges the gap between abstract theory and observable phenomena, linking the behavior of photons and electrons to the technologies and natural processes that shape the world around us. By understanding that energy is transferred in discrete units, scientists not only solved long-standing experimental puzzles, but also unlocked the potential for transformative innovations that continue to define the modern era. The discovery of photon energy quantization thus represents a cornerstone of quantum physics, highlighting the profound interplay between theory, observation, and technological application. The discovery that energy is emitted and absorbed in discrete units revolutionized the understanding of light and the behavior of matter, reshaping physics in ways that continue to resonate today. Classical physics, with its elegant and deterministic laws, treated energy as a continuous quantity, capable of varying smoothly across any value. Light, for example, was understood purely as a wave, spreading endlessly through space, its intensity determining the energy it carried. This model worked well for macroscopic observations such as reflection, refraction, and diffraction, but it failed spectacularly when scientists examined microscopic phenomena. The emission spectra of heated objects, photoelectric effects, and the behavior of electrons and atoms all indicated that energy does not flow in a continuous manner, but is instead transferred in fixed, indivisible amounts known as quanta. This insight emerged from meticulous experimentation, particularly the study of Blackbody radiation and atomic spectra. Heated objects emit light in characteristic patterns, with specific frequencies and intensities, which could not be explained by classical laws predicting smooth, continuous energy emission. These observations suggested that atoms emit radiation in precise increments rather than gradually, pointing to an underlying quantization of energy. By introducing the idea of discrete energy packets, scientists were able to resolve inconsistencies and predict the behavior of matter and light with remarkable accuracy. This marked the beginning of a fundamental shift in the understanding of the natural world, bridging the gap between observable phenomena and theoretical models. The emission and absorption of energy in discrete units also provided a mechanism for explaining atomic stability. Electrons within atoms do not spiral continuously toward the nucleus, as classical physics would suggest. Instead, they occupy specific energy levels, moving between these levels only when absorbing or emitting a quantum of energy that matches the exact difference between initial and final states. This framework clarified why atoms are stable and why they emit light at discrete frequencies, forming the characteristic spectral lines of elements. The quantized transfer of energy, thus, offers both a theoretical and practical explanation for phenomena that had long puzzled scientists, from atomic spectra to chemical behavior. Understanding energy, Quanta also shed light on the behavior of light as both a wave and a particle. Experiments such as the photoelectric effect demonstrated that light imparts energy in discrete amounts, with the energy of individual photons proportional to their frequency. This particle-like behavior exists alongside wave properties, such as interference and diffraction, revealing the dual nature of light. This duality, while initially counterintuitive, became a cornerstone of quantum mechanics, allowing scientists to reconcile observations that classical physics could not explain and providing a consistent framework for describing electromagnetic radiation. The quantization of energy is essential to many technological applications. Lasers, for instance, rely on electrons transitioning between discrete energy levels, emitting photons with precise energies and wavelengths. This controlled emission produces coherent light that has revolutionized fields ranging from medicine to telecommunications and industrial manufacturing. Similarly, solar cells exploit the discrete energy of photons to excite electrons across energy gaps, converting light into electricity. LEDs, fluorescent lighting, and even digital imaging sensors operate on the principle that energy is exchanged in quantized units, demonstrating the deep connection between abstract quantum principles and tangible technological innovations. The concept of energy quanta also underpins modern atomic and molecular spectroscopy. By observing the frequencies of light absorbed or emitted by atoms and molecules, scientists can determine their structure, composition, and energy states. This technique allows astronomers to analyze the chemical makeup of distant stars, study molecular interactions in complex systems, and investigate fundamental physical constants. The discrete nature of energy exchange ensures that these observations are precise, predictable, and reproducible, providing a robust tool for scientific exploration and discovery across multiple disciplines. On a deeper level, the quantization of energy challenges classical assumptions about continuity and determinism. At microscopic scales, energy transfers are not arbitrary. They follow strict rules dictated by quantum mechanics. This introduces a probabilistic dimension to physics, where the exact timing of transitions may be uncertain, even though the energy involved is precisely defined. Such insights fundamentally alter our understanding of causality, motion, and the flow of energy, demonstrating that the universe at its most fundamental level operates according to principles that are discrete, structured, and mathematically elegant. Moreover, recognizing that energy is quantized provides a foundation for understanding chemical bonding, electron excitation, and a wide range of phenomena in condensed matter physics. Electrons move between discrete energy states within atoms and molecules, absorbing or releasing energy as needed. This behavior governs the properties of materials, the outcomes of chemical reactions, and the mechanisms behind conductivity, magnetism, and luminescence. The quantized transfer of energy is thus not merely a theoretical concept, but a practical principle with implications for chemistry, material science, electronics, and biology. Ultimately, the realization that energy is exchanged in discrete units reshaped the scientific world. It solved long-standing experimental puzzles, provided a coherent framework for understanding light and matter, and enabled the development of technologies that define modern life. By revealing the ordered, quantized structure of energy interactions, scientists could move beyond the limitations of classical physics, opening the door to quantum mechanics and a deeper understanding of the universe. This insight continues to influence research, from quantum computing to photonics, illustrating the enduring power and relevance of the principle that energy is not continuous but comes in discrete, indivisible packets that govern the behavior of the microscopic and macroscopic world alike. The role of quantum theory in understanding atomic spectra represents a pivotal advancement in the study of matter, allowing scientists to decode the intricate patterns of light emitted and absorbed by atoms. Atomic spectra are composed of discrete lines, each corresponding to a specific wavelength or frequency of light. These lines fascinated scientists for decades, as classical physics could not explain why atoms emitted light at only particular frequencies rather than across a continuous spectrum. The discovery that energy within atoms is quantized provided the key to unlocking this mystery, revealing that electrons occupy specific energy levels and that transitions between these levels produce photons with precise energies. This insight transformed the understanding of atomic structure and laid the groundwork for modern quantum mechanics. The emission of spectral lines occurs when electrons move from higher energy levels to lower ones within an atom. Each transition involves the release of a photon, whose energy exactly matches the difference between the initial and final energy states. Conversely, absorption occurs when electrons jump to higher levels after absorbing photons of matching energy. This precise correspondence between energy differences and photon frequencies explains the existence of discrete spectral lines and provides a direct window into the internal structure of atoms. Observing these lines allows scientists to determine the arrangement of electrons, the spacing between energy levels, and the unique identity of each element, giving rise to a powerful method for chemical analysis and astrophysical investigation. The study of atomic spectra also illuminates the concept of quantization in a tangible way. Before the advent of quantum theory, electrons were thought to orbit the nucleus in arbitrary paths, with energy varying continuously. However, experiments revealed that electrons can occupy only certain allowed energy states, with no intermediate positions between them. This discrete behavior is directly reflected in the emission and absorption of light, as only photons with energies corresponding to these specific transitions are produced or absorbed. The quantized nature of electron energy levels resolves long-standing puzzles about atomic stability, explaining why electrons do not spiral into the nucleus and why atoms maintain distinct chemical identities. The introduction of quantum principles to atomic spectra also provided a framework for understanding more complex phenomena, such as fine and hyperfine structures. These subtle variations in spectral lines result from electron spin, magnetic interactions, and relativistic effects, all of which can be accounted for using quantum mechanics. By applying these principles, scientists can predict the behavior of atoms with remarkable precision, from simple hydrogen atoms to complex multi-electron systems. Spectroscopy, informed by quantum theory, thus became an indispensable tool in both experimental and theoretical physics, bridging observation and calculation. Technological applications of understanding atomic spectra are widespread and profound. Lasers, for example, rely on electrons transitioning between specific energy levels to produce coherent, monochromatic light. The precision with which these energy levels are defined enables the production of light with exact wavelengths, which is essential for applications in medicine, communications, manufacturing, and scientific research. Similarly, spectroscopy informs the design of LED, fluorescent lights, and other devices, allowing engineers to manipulate electron transitions to generate light efficiently. On a larger scale, atomic spectra serve as a means of studying distant stars and galaxies, as the absorption and emission lines in starlight reveal their composition, temperature, and movement. The quantized understanding of atomic spectra also informs the broader field of quantum mechanics, illustrating the fundamental principles of energy quantization, wave, particle duality, and probabilistic behavior. Electrons exhibit both particle-like and wave-like properties, with their allowed energy states corresponding to standing wave patterns around the nucleus. The spectral lines are a direct manifestation of these quantum patterns, linking theoretical models to observable phenomena. This connection provides a framework for predicting chemical reactivity, electron configurations, and the properties of materials, making quantum theory a unifying principle across physics and chemistry. Moreover, the study of atomic spectra highlights the interplay between experimentation and theory in scientific progress. Spectroscopic observations provided precise, reproducible data that challenged classical models and demanded new explanations. The introduction of quantized energy levels offered a theoretical framework that could be tested and refined through further experimentation. This iterative process exemplifies the scientific method, demonstrating how empirical evidence and conceptual innovation work together to advance understanding. Philosophically, the quantized nature of atomic spectra challenges classical notions of continuity and determinism. The discrete energy levels and the probabilistic nature of electron transitions reveal a universe in which certainty at the microscopic scale is limited, and where precise prediction must account for probabilities rather than deterministic paths. This shift represents a profound change in perspective, highlighting that nature is not always intuitive and that the behavior of matter and energy at the smallest scales operates according to principles that are mathematically rigorous, yet often counterintuitive. Ultimately, the study of atomic spectra through the lens of quantum theory exemplifies the power of quantization to reveal hidden structures within nature. By explaining the precise energies of electron transitions, scientists could decode the patterns of light emitted and absorbed by atoms, solve long-standing paradoxes, and develop technologies that rely on controlled electron behavior. Atomic spectra serve not only as a window into the quantum world, but also as a practical tool for scientific discovery, enabling applications in fields ranging from chemistry and physics, astronomy, and engineering. The understanding of spectral lines stands as a testament to the transformative power of quantum principles, illuminating the deep structure and ordered complexity of the universe. The development of quantum theory fundamentally reshaped our understanding of matter and energy, particularly in relation to atomic and subatomic phenomena. One of the most profound insights arising from this theory is the realization that energy is not continuous, but exists in discrete units, or quanta. This principle underlies the behavior of electrons, photons, and all microscopic particles, providing a framework for understanding processes that classical physics could not explain. By quantizing energy, scientists were able to resolve long-standing puzzles in atomic behavior, light emission, and chemical interactions, bridging gaps between observation and theory and opening the door to a deeper understanding of the universe. At the atomic level, the quantization of energy explains why electrons occupy specific energy levels rather than moving arbitrarily around the nucleus. Classical models, which envisioned electrons as tiny planets orbiting in continuous paths, failed to account for the stability of atoms. According to these models, electrons should radiate energy continuously and spiral into the nucleus, causing atomic collapse. However, quantum theory showed that electrons are restricted to discrete energy levels, and transitions between these levels occur only when energy is absorbed or emitted in precise amounts. These transitions give rise to observable phenomena such as spectral lines, where atoms emit or absorb photons with energies corresponding exactly to the difference between energy levels. This quantization ensures atomic stability and explains why each element has a unique spectral fingerprint. The principles of quantum mechanics also reveal the dual nature of light and matter. Light behaves both as a wave, capable of interference and diffraction, and as a particle transferring energy in discrete packets called photons. Similarly, electrons and other particles exhibit wave-particle duality, displaying both localized particle behavior and wave-like properties, such as forming standing wave patterns around the nucleus. This duality challenges classical intuitions and provides a more complete understanding of microscopic phenomena. It explains experimental results that had long puzzled scientists, from the photoelectric effect to electron diffraction, and demonstrates that the fundamental constituents of the universe cannot be fully described using classical concepts alone. Quantum theory also introduced probabilistic principles into the description of microscopic events. While the energy of transitions and interactions is precisely defined, the exact timing and position of individual events are inherently uncertain. This probabilistic nature is encapsulated in the concept of the wave function, which provides a mathematical description of the likelihood of finding a particle in a particular state. Unlike classical mechanics, which predicts definite outcomes, quantum mechanics operates in terms of probabilities, allowing for accurate predictions of ensembles of particles while acknowledging uncertainty in individual events. This perspective revolutionized the scientific understanding of determinism and introduced a fundamentally new way of modeling reality. The quantization of energy and the probabilistic behavior of particles have profound practical implications. Lasers, for instance, operate by inducing electrons to undergo transitions between energy levels, emitting coherent photons with precisely controlled frequencies. Solar panels exploit the discrete energy of photons to excite electrons across energy gaps, producing electrical current. Fluorescent lights, LEDs, and other modern technologies similarly rely on controlled quantum transitions. Even fundamental research, such as particle accelerators and quantum computing experiments, depends on the principles of energy quantization and probabilistic interactions. These technologies illustrate how abstract theoretical concepts in quantum physics translate directly into practical applications that shape modern life. The study of quantized energy levels also informs spectroscopy, a technique essential for probing atomic and molecular structure. By analyzing the wavelengths of light absorbed or emitted by substances, scientists can determine chemical composition, temperature, density, and motion. This method allows astronomers to study distant stars and galaxies, chemists to explore molecular interactions, and physicists to investigate the properties of fundamental particles. The discrete nature of energy transitions ensures that these measurements are accurate and reproducible, providing a precise tool for understanding matter on scales ranging from the microscopic to the cosmic. Furthermore, quantum theory has expanded scientific understanding of chemical bonding and molecular behavior. The rules governing how electrons occupy energy levels determine how atoms combine to form molecules, dictating bond strengths, reactivity, and molecular geometry. Quantum principles explain why some reactions release energy, others absorb it, and why certain molecular configurations are more stable than others. This understanding underpins chemistry, materials science, and molecular biology, providing a foundation for innovations in pharmaceuticals, nanotechnology, and advanced materials. Philosophically, quantum mechanics challenges classical notions of continuity, certainty, and determinism. The discrete nature of energy and the probabilistic character of particle behavior reveal that the microscopic world operates according to principles that are fundamentally different from macroscopic experience. The behavior of light, electrons, and atoms demonstrates that nature is structured, ordered, and yet inherently unpredictable in detail, highlighting the elegance and complexity of the universe at its smallest scales. Ultimately, the quantization of energy and the probabilistic nature of quantum mechanics provide a unified framework for understanding atomic and subatomic phenomena. By explaining why electrons occupy discrete energy levels, how light interacts with matter, and why atoms are stable, quantum theory resolved paradoxes that classical physics could not address. These principles form the basis for modern technologies, from lasers to quantum computers, and enable scientists to explore the universe at both microscopic and cosmic scales. The insights derived from quantized energy continue to guide research, revealing the subtle, structured, and fascinating architecture of the natural world. The uncertainty principle represents one of the most profound and conceptually challenging discoveries in quantum physics, fundamentally altering our understanding of measurement, observation, and the nature of reality itself. Classical physics assumed that the properties of particles, such as position and momentum, could be measured simultaneously with arbitrary precision. It was believed that, in principle, the more accurately one measured a particle's position, the more accurately its momentum could also be known, and vice versa. Yet, experiments and theoretical developments in the early 20th century revealed that this assumption fails at microscopic scales. The uncertainty principle, formalized mathematically by Werner Heisenberg, asserts that certain pairs of physical properties, like position and momentum, cannot both be precisely determined at the same time. This principle is not a limitation of measurement tools or experimental technique, but a fundamental feature of the quantum world, illustrating the inherent indeterminacy of nature at its smallest scales. At the heart of the uncertainty principle is the recognition that particles exhibit both wave-like and particle-like properties. An electron, for example, can be described as a particle localized in space or as a wave extended over a region. The more precisely the position of the electron is known, the less precisely its momentum can be described, because a localized wave packet necessarily contains a superposition of different momenta. Conversely, a wave with a well-defined momentum is spread out in space, making the exact position of the particle uncertain. This duality underpins the fundamental limits imposed by the uncertainty principle and demonstrates that nature does not permit absolute knowledge of all properties simultaneously. The implications of this principle reach deeply into both theory and experiment, redefining how scientists understand the behavior of microscopic systems. The uncertainty principle also provides an explanation for the probabilistic nature of quantum mechanics. Unlike classical systems, where the future trajectory of a particle can be predicted exactly if initial conditions are known, quantum systems can only be described probabilistically. The wave function, which encodes the probability distribution of a particle's properties, reflects the limitations imposed by the uncertainty principle. Measurements yield specific outcomes, but the exact result cannot be predicted with certainty, only the likelihood of occurrence. This probabilistic framework reconciles the apparent randomness observed in quantum phenomena with a rigorous and predictive mathematical theory, providing a foundation for understanding atomic and subatomic processes. One of the most important consequences of the uncertainty principle is its role in explaining atomic stability. Electrons in an atom cannot collapse into the nucleus because their position and momentum are subject to uncertainty. If an electron were confined to the nucleus, its momentum would become extremely uncertain, giving it enormous kinetic energy that prevents such collapse. This principle thus ensures that electrons occupy stable, discrete energy levels, providing a natural explanation for atomic structure without the need for additional ad hoc assumptions. It also explains the zero-point energy observed in quantum systems, the residual energy that persists even at absolute zero temperature, which classical physics cannot account for. The uncertainty principle has profound implications for measurement and observation. In quantum mechanics, the act of measurement affects the system being observed. Observing the position of a particle with high precision inevitably disturbs its momentum, and measuring momentum precisely disturbs position. This intrinsic interaction challenges the classical notion of an independent, objective reality, highlighting that in the quantum realm, the observer and the observed are intimately connected. It is not merely a technological limitation, but a reflection of the fundamental structure of nature. Technological applications of the uncertainty principle are numerous and significant. It underlies the behavior of semiconductors, which form the backbone of modern electronics, by explaining the limits of electron localization and conduction. Quantum tunneling, another phenomenon rooted in uncertainty, allows particles to penetrate energy barriers, enabling the operation of devices such as tunnel diodes and scanning tunneling microscopes. In nuclear physics, the principle explains the stability of atomic nuclei and the energies involved in radioactive decay. Even emerging technologies, such as quantum computing and quantum cryptography, rely on the inherent uncertainties and probabilistic nature of quantum systems to encode, manipulate, and secure information. Philosophically, the uncertainty principle challenges traditional deterministic views of the universe. It demonstrates that at microscopic scales, nature is inherently probabilistic, and that precise predictions of all physical quantities are impossible. This insight requires a re-evaluation of cause and effect, determinism, and the limits of human knowledge. It emphasizes that the universe is not a rigidly predictable machine, but a dynamic, probabilistic system governed by fundamental principles that defy classical intuition. In addition, the uncertainty principle has provided insights into fundamental questions in physics, such as the behavior of particles in fields, the limitations of simultaneous measurements of conjugate variables, and the energy fluctuations inherent in quantum systems. It serves as a guiding principle in the study of quantum optics, particle physics, condensed matter physics, and cosmology, influencing research into phenomena ranging from the behavior of electrons in materials to the properties of black holes and the origins of the universe. Ultimately, the uncertainty principle exemplifies the counterintuitive, yet mathematically rigorous, nature of the quantum world. It reveals the limits of knowledge, the probabilistic structure of reality, and the intimate connection between measurement and system behavior. By defining the fundamental boundaries of what can be known, it provides a framework for understanding atomic stability, energy levels, and the behavior of all microscopic systems. This principle not only reshaped the philosophy of science, but also enabled practical technological advances, illustrating the profound interplay between theoretical insight and empirical observation in the ongoing quest to understand the universe. The implications of quantum mechanics for modern technology and scientific innovation are vast and transformative, reflecting the profound influence of principles such as energy quantization, wave, particle duality, and the probabilistic nature of matter. The discoveries that emerged from early quantum theory provided not only a deeper understanding of the microscopic world, but also practical tools that underpin many aspects of contemporary life. From computing and communication to medicine and energy, the insights derived from quantum physics continue to shape the technologies that define the modern era. Understanding these principles allows scientists and engineers to harness the behavior of particles and energy at their most fundamental levels, unlocking possibilities that were once the realm of imagination. At the core of these applications is the recognition that energy and matter behave in discrete, predictable ways according to quantum rules. Electrons occupy defined energy levels, photons carry quantized energy, and the properties of particles are constrained by principles such as the uncertainty principle. These rules, while counterintuitive, allow for precise control over atomic and subatomic systems. In semiconductors, for example, the behavior of electrons within energy bands is dictated by quantum mechanics, enabling the creation of transistors, diodes, and integrated circuits. These components form the backbone of all modern electronics, from smartphones to supercomputers, and demonstrate the direct translation of quantum principles into practical technological innovations. Quantum mechanics also underpins the operation of lasers, which rely on controlled transitions of electrons between energy states to emit coherent light. Lasers have revolutionized medicine, enabling minimally invasive surgeries, precise eye treatments, and advanced imaging techniques. In telecommunications, lasers transmit information over optical fibers with incredible speed and fidelity, forming the foundation of global internet infrastructure. In industry, lasers are employed for cutting, engraving, and manufacturing at microscopic scales, demonstrating the wide-ranging impact of quantum-based technology. The ability to manipulate energy levels and photon emission illustrates how the abstract principles of quantum physics can produce concrete, transformative applications. In addition, quantum theory has enabled the development of medical imaging technologies, such as MRI, magnetic resonance imaging, which relies on quantum spin states of atomic nuclei. By understanding how particles respond to magnetic fields and energy absorption, scientists developed techniques to generate detailed images of internal body structures without invasive procedures. Similarly, radiation therapies for cancer treatment exploit the interaction of high-energy particles with biological tissues, guided by quantum principles that govern energy deposition and particle behavior. These applications highlight the life-saving potential of quantum discoveries and their integration into practical healthcare solutions. Quantum mechanics also forms the foundation of quantum computing, an emerging field that promises to revolutionize information processing. Unlike classical computers, which operate with binary bits, quantum computers use qubits that exploit superposition and entanglement, enabling computations on multiple states simultaneously. This ability dramatically increases computational power for specific types of problems, such as cryptography, material modeling, and complex simulations. The development of quantum algorithms and error correction techniques depends entirely on a deep understanding of quantum principles, demonstrating that theoretical insights can drive entirely new technological paradigms. Energy technology has also benefited from quantum discoveries. Photovoltaic cells, which convert sunlight into electricity, operate by exciting electrons across energy gaps in semiconductors, a process governed by the quantization of energy. The efficiency of these devices depends on precise control of electron behavior, band structures, and photon absorption, all rooted in quantum mechanics. Similarly, advances in energy storage, superconductivity, and materials science rely on understanding electron behavior, wave functions, and energy quantization, enabling innovations that support renewable energy, efficient power grids, and advanced electronics. In scientific research, quantum principles allow the exploration of phenomena previously inaccessible to classical methods. Techniques such as spectroscopy, electron microscopy, and particle accelerators rely on quantum behavior to probe the structure of matter at atomic and subatomic scales. These tools have expanded knowledge across physics, chemistry, biology, and cosmology, from discovering new materials to studying distant stars and galaxies. Quantum mechanics thus provides both a conceptual framework and a practical toolkit for advancing human understanding of the universe. The philosophical impact of these discoveries is also significant. Quantum mechanics challenges traditional notions of determinism and objective reality, highlighting the role of probability, measurement, and observation in defining the behavior of particles. While this probabilistic framework initially appeared unsettling, it has proven remarkably effective in predicting and controlling natural phenomena. By embracing the inherent uncertainty and wave-particle duality of matter, scientists have developed technologies that operate with unprecedented precision and versatility, demonstrating the power of theory-driven innovation. Ultimately, the applications of quantum mechanics illustrate the seamless interplay between fundamental research and technological advancement. Insights into energy quantization, wave-particle duality, and atomic stability have translated into practical devices and methodologies that shape everyday life, from electronics and communication to medicine and energy. The ongoing exploration of quantum phenomena promises even greater innovations, including quantum networks, advanced sensors, and transformative computational capabilities. By harnessing the principles of the microscopic world, humanity continues to unlock new frontiers of knowledge and capability, illustrating that the legacy of quantum discoveries extends far beyond theory, profoundly shaping the modern era and future possibilities.